a lot of times we have t is equal to time. And this is the independent variable. So when we write something like s of t, that's the position function. When we write v of t, that's the velocity function. When we write a of t, that's the acceleration function. So how do we move from one to the other? Well, if you want to go from position to velocity, you simply differentiate with respect to t. That means you take the derivative. And then if you wanted to go from the velocity to the acceleration, you take the derivative again. Okay. So how does this make sense? The position is how far you've gone. You take the derivative with respect to time, you're saying, how far have you gone per unit time? So I hope that going from position to velocity makes sense. I mean, this is what 1.4 was all about. When you think about what it means to differentiate the velocity with respect to t, we're saying, how fast is the velocity changing? So, you know, when you drive your car and your car's on cruise control, it's going at a steady speed, and you don't really feel anything. It just feels like you could just sit there and eat. I mean, you shouldn't, but the car is just moving at this very steady speed. So that's a constant velocity. So what does it feel like when the velocity changes? When the velocity changes, that means that you're going faster and faster and faster. So like, you know, when you're trying to merge onto the 110 freeway and there's like a stop sign there and your velocity is 0, then you floor it and then your velocity starts increasing. You go from 0 to 60, right? What does that feel like? That feels like you're getting pushed back into the seat of your car. That feeling is what acceleration is. All right. So this is a long way of saying the acceleration is the second derivative of the position function. If you took the derivative of the position twice, you get the acceleration. I think you guys can do example 9. Find the first derivative first. So find s prime. And for example 9, and let me know what you get. Okay. I started this problem. I hope you can see on the screen. In the past, I wrote an extra step to distribute, but in this case, I distributed already for this part right here, just to save myself some writing. So let me just continue on. There's a limit as h goes to 0. Got the 1 over h in front here. I got to FOIL this guy. So this will be 3 times t squared plus 2th plus h squared minus 4t minus 4h. And then I can see, I can already cancel some of this stuff. The +1 and the -1 cancel. So I end up with minus 3t squared plus 4t, like this. Okay. Now I'm going to distribute, so I get the limit as h goes to 0, 1 over h. We're going to get 3t squared plus 6th plus 3h squared minus 4t minus 4h minus 3t squared plus 4t. Okay. All right, let's see if things cancel out for us. We got the 3t squared that cancels out with a minus 3t squared. We got a 4t, minus 4t and a plus 4t canceling out. And it seems like everything else involves an h. H here, h there, h there. So I'm going to factor out the h. So when I factor out the h, I get the limit as h goes to 0. Get an h on top with an h on bottom. And it's 6t plus 3h minus 4. So these h's cancel out. And this h goes to 0. And then you're left with 6t minus 4. Is there any questions about that? That's our first derivative. This question actually asks for the acceleration. So we want this guy was the velocity actually. So we want the acceleration. That's going to be the derivative of the velocity, which is the second derivative of the position. Now, you can go ahead and use the definition of the derivative, but I claim that we can already just look at this function and tell what the derivative is going to be. What do you guys, just by looking at this, what's the derivative? That's correct, it's 6. And why is it 6? Because this is just a line. So the tangent line to the line is the line itself. So all I need to do is just look at the slope. To find the second derivative of t. Okay. So so that's what we got for that guy. Is there any questions about this?